Hi. So could you connect well?
Hello.
I hear some noise, but okay, Chiro, I'm gonna make you co-host.
Hello.
I also oh no. Yeah, Cheng-An, I don't like. Yeah, I didn't hear you yet. Oh, there you are. Okay.
It's horrible.
I can see you fine. Okay, do you want to share some slides or try something?
Yes. Let me see. Oh, I cannot do full screen.
Okay, that looks good.
This is blocking. How do I remove this?
We usually wait 5 minutes because people take time to connect and everything.
Sure.
I'm also recording the meeting. We put it in YouTube. Are you okay with that? Or
Sure.
okay, thank you. Well, I don't know. I don't think we put any of this on YouTube, but maybe we will. Sorry, but I'm gonna record it. That's for sure. Yes, it's a group of people that logged in, but we're still gonna wait a few minutes. Maybe some more are coming.
Hello, everyone.
Hello, it's okay.
Hi.
Hello.
Yeah, I was thinking to wait to 5 minutes past, like a couple of minutes more. Okay, so I think we're very happy to have Cheng-An, which, if I'm not mistaken, is in Taiwan. So we have an international journal club. And then, as usual, feel free to interrupt. This is very informal. And we try to stick to 1 hour, but there's always extra time for questions and other things if you want to discuss. And please mute if your microphone, if you're not speaking. You can leave the camera on or off. It doesn't matter, I think. And the other thing is I'm recording the meeting. I'm not sure what we're going to do with the recording, but we could post it online or just have it for our, if somebody wants to go back and look at the top. Okay, so go ahead. Keiichiro and Uday are co-hosts. I'm telling you, so if you want for them, I mean, I'm telling them that if you can help me, somebody tries to log in and I don't see it, or somebody posts something in the chat that needs some help, maybe you can help me with that. Okay, so let's just go ahead.
All right. Hello from the other side. Today, I'm Cheng-An. I'm working with Professor Cheng-Long Hong in experimental AMO. And today I'm going to talk about a paper in 2019 and following paper in 2020 is the first paper is observation of the thermal Hawking radiation and temperature in an analog black hole. And so feel free to interrupt me for asking questions. And I am not an expert of a black hole, so but this system is since in a ultra cold atomic system, so I think it would be interesting to see and to know, and also in toward the end of this journal club, I will briefly introduce what we our ability in Purdue. Oops. Okay, so Hawking radiation, I think everyone here is probably know better than me. The Hawking radiation is that if there's a black hole, and if we know from vacuum fluctuations, there's a particle and antiparticle create and annihilate in space. And if one of the particle fall into the black hole, and since fall into the event horizon, it cannot escape. So the other one will leave and becomes Hawking radiation. And this brings us some interesting questions, such as the so-called information paradox, is that if we know, since the particle and antiparticle generated from the vacuum fluctuation, they are entangled. So if we can somehow measure the Hawking radiation, can we know the information inside the black hole, inside the event horizon? And so there are some approach. Well, since as of today, there's no human technology can measure the real Hawking radiation from a real black hole in the universe. There are people proposing idea using co-atoms or other systems to try to measure the analog or try to simulate a similar phenomena. The idea is the following. We have a co-atoms at the background, and we create event horizon. I will talk about how people do this. And so if there's a vacuum fluctuation around the horizon, and one of the particle fall into this part and one traveling toward this part, and if this part, the background co-atoms has let me use the mouse. Has the velocity which so if this part, the sound speed is is faster than the background superfluid flow, then this particle can escape. And if this particle, somehow we engineer the sound speed, is slower than the background flow, then anything happens in this part will not be able to travel through this artificial event horizon. And so what we're gonna do is doing things like this. We have a background superfluid flow, and naturally the vacuum fluctuation will generate entangled pairs. And we do a measurement at outside, inside these artificial horizon. And at this part, the flow is faster than the particle, the travel speed of the particle. So everything here will not be able to travel through this horizon. So this part is inside the black hole, and this part is considered outside the black hole. Okay. So this idea is firstly proposed by Professor Unru in UBC, and so basically the idea is that we can use this hydrodynamics idea, and here the V is the velocity of the flow, and the low is the density, and the C is the the C is the speed of the sound in the flow, which is the particle travel speed, and we can calculate so that at the final form is can be analog to this black hole, the real black hole matrix. And we can also use this to derive the effective Hawking temperature by this way. So we get the effective Hawking temperature, and this is proportional to the so-called surface gravity, which is the speed gradient of the speed of the horizon traveled and the sound speed traveled. And this is effective Hawking radiations. So experimentally, how people do this? There's a group in Israel which has been consistently working on this project. This is, so initially in 2014, they observed the so-called black hole laser, which is like, the idea is like, if they excited a mode inside the black hole, and these black hole, if they generate it's kind of a black hole and white hole area. This is lower sound speed part, higher sound speed part, higher sound speed part. So the pseudoparticle, which is a phonon in this case, can bounce back and forth. So this part is acting like a laser cavity, so they can observe a black hole laser in this case. And this is what they observe, like this way, and they claim this excitation is the black hole laser. And then later in 2016, they observed the Hawking radiation and its entanglement, and this part is the so-called density-density correlation. Later we will introduce. So basically, dark part, which is a negative density-density correlation, the thin part here indicate the Hawking radiation and its partner inside and outside the event horizons. And this is their evidence, and they also use these criteria to calculate the non-separability, and claim this non-separability part indicate the entanglement of the particle inside and outside the Hawking radiation and its partner. And today we will see everything here, and but not the entanglement part. So in this paper.
So excuse me, so this may not be directly related to the topic today, but I'm curious about these black hole lasers. Yeah, well, does a black hole laser have any advantage compared to the laser we have using other schemes?
No. So in my opinion, this is kind of a self-amplifying of quasi-particle. So you drag a boundary, which you will see very soon how they experimentally do it. Drag a boundary, and you have a collective excitation of a quasi-particle, which is a phonon in the BC. And to me, this is a kind of general case. If you do in other systems, you will see collective excitations. I don't see really advantage, but the beautiful part, which is not in that paper actually, is that if the excitation is originally from the vacuum fluctuation, and that could simulate possibly, which we don't know, possibly simulate a charged black hole, because it contributes to another mode, if we somehow one day can measure a real Hawking radiation from a black hole, this indicated, okay, this is a charged particle, which is kind of a white hole to me inside a event horizon. Yeah.
Okay.
Okay, so experimentally, what they did is like this. They trap BC, both Einstein condensate in quasi 1T trap, and they create a boundary by the potential. So the potential is engineered with a step. So this image is kind of indicator, the color indicates the density of the atoms. This is actually a phase construct, but basically this is a higher density part. And so if they drag this boundary, which means they drag the potential state, and they change the density on different side. And because the sound speed in this system is that this part with lower density has a lower sound speed, and this part has, sorry, the other way. This part has a higher sound speed, and this part has a lower sound speed. So when they drag, and then when you are at a co-moving frame with these potential dragging, and you will effectively see an area which any particle cannot escape, like this way. And at the bottom is a real situation. I'll just give you a sense of how potential looks like. It's actually a very broad harmonic trap, and with little small bump potential generated by a Booty tuned laser, which generates a repulsive force to this atomic cloud. And later I will tell you why this matters to me. So it looks like this. And so this is the density, average density over many shots. And this is a calculated sound speed. And if we are at a co-moving frame, this will be the event horizon we care. So this is a static for us. And the flow is from left to right. Flow is like flowing like this way. So this is outside the black hole, this is inside the black hole. And from this, the gradient of this, we can calculate the previous term and to estimate the Hawking temperature. So the Hawking temperature, the estimate is the green measurements, which is the first term in the previous equation, in the blue is the second term that add up becomes the black, which is here you can see it's super noisy, and so we leave it with what it is. So they estimate that Hawking temperature will be like this, and this is just a comparison. Later they will show it consistent with the simulation theory and other measurements. Okay. So one way to, they have a preliminary test or preliminary measurement. And in my opinion, this preliminary measurement is done for one reason, that they want to know the V and C, which the speed of sound, especially speed of sound, and V, which is the effective drag for in their system, because the density is very inhomogeneous in every place. So these two quantities are not, not very straightforward to measure, directly measure or no. So what they did is the following. They oscillated the horizon. They have a horizon and they oscillate. And so they artificially create wave traveling toward both sides. And so they can do correlation function, they can do density correlations, and they extract the dispersion like this from their oscillating horizon experiment. So this is assuming this is green. Ripple is how they oscillate the horizon. They generate waves, and this is just assuming. So this is the dispersion they measure, and there are two modes. One is outside the event horizon. There's only one mode with positive energy, and is traveling outward away from the event horizon. And inside event horizon, there are two modes. One with positive energy, one is negative energy. And what people, the Hawking radiation and its partner, people are talking about is the partner mode, which is this. And this is the negative energy dispersions. And this is positive energy dispersion, which is just another mode or another solution in variable self energy dispersion, if you take that way. And this is not, this is, they call it co-propagating mode. And this is a mode which would exist in this system in the experiment, but not the entangled mode or the mode we are really looking at. It's not a partner, Hawking and its partner. Okay. And from there, this is the, the signal they are looking at, and they do the Fourier transform at this green box, and so they can get the mode in the momentum space. And where they show here is that again, this the hollow dot, the circle indicates the co-propagating mode, and the solid dot indicate the partner mode. And they say in a higher K is deviated from variable dispersion and then going to a free particle, which free particle here is just a parabolic curve here. And they say this part may just excite higher, because a higher K excite a higher mode in this condensate. I take it as a artifact. Okay. Any questions so far?
Sorry, I didn't understand. So how did the measure omega? Well, K can be obtained from basically from this Fourier transform. Okay,
Yeah.
but how
This is the
energy
other
or the
way.
frequency was obtained?
This is actually that way. They change omega and they measure K. They are
Oh.
able to get K from Fourier transform. And
I
they
see.
measure.
So this,
Yeah.
so this omega is precisely the oscillate. Well, it comes from the oscillating horizon. Okay, on
Correct.
top of in the co-moving frame, this horizon is actually oscillating sinusoidally, right?
Yes. Yes.
Okay.
Yes.
I see. This is okay. This is oscillation frequency.
Yeah.
Okay, thanks. Mm-hmm.
So in my opinion, what they do this is just want to get this dispersion, and this is do well in a reverse step. It's kind of they know, or they are expecting what the signal will be, and they measure dispersion so that later they can convert it back to omega. And experimentally, I don't really, I'm not really confident about this method. It's kind of you expect where you will see the signal, but anyway, that's how they did that. And I agree with that. This is a challenging experiment, so perhaps that's the way to find a signal. Anyway, so this is basically the result. So this is without oscillating the horizon. It basically just drag the potential, drag the horizon, but they don't oscillate. So the signal here, the density correlations signal here is the possible signal from vacuum, the particle antiparticle generated from vacuum fluctuations. That's how they claim. So this is very weak signal, and here is the simulation. That the green line is the partner mode that we just mentioned, and the red line is the co-propagating mode, which is the signal, which is not the signal we are looking at. So they compare this and a simulation and say, okay, this is the Hawking radiation, basically like this way. And they do this, the G2, the second order correlation function defined like this way, basically is just do at this part and perpendicular to the density correlation, negative density, this is darker, so this negative density correlation lines. Along this line, they do G2 correlation functions, and the cassette here is heating length. Basically, this is a length scale in ultra cold atoms, and LO is the region they do Fourier transform. And from negative G2 function, it indicate this is a non-classical correlations. So it's just another data, and this is the simulation with the experimental parameters, and sort of agrees well. But again, this is not the indications of the entanglement. To see the entanglement, we need to go back to the criteria we mentioned in the second slides. This is just tell us this is a non-classical correlations. And why the curve is not, sorry, let me, oops, okay, I know how to change this. So why this is not symmetric, I don't have a very straightforward intuitive explanations. So this is from the other paper from the same group. This schedule can be calculated, and it just show us that this is not symmetric is kind of makes sense, but honestly, I don't know why. And the rate is the hydrodynamics, which the intuitive pictures we have. And the solid black line is the calculation from the Bogoliubov theory, and that's it. So this is the older result talked in this paper, discussed in the paper. So basically, it's all about the experimental evidence of analog Hawking radiation in their systems. So they have observed this in 2015, 2016. The only difference in this 2019 paper is that they have better resolutions, more stable systems, so they can extract the temperature better. So how they extract the temperatures and to see more convincing evidence is the final figures of this in this paper, which again, this is the green dot is the oscillating horizon experiment. This is the green dot, and red dot is also from the oscillating horizon. And only the background here, the grayscale background, is the correlation of a correlation function in K-space, inside and outside the horizon. So what they are saying here is that the correlations follows Hawking and partner mode they are expecting, and nothing, no signal along this Hawking and propagating line they know. So they say, okay, yeah, so this is the real signal they want, the Hawking and his partner. And on the other hand, they can also check this figure. This is S is a static structure factors, and they calculate this quantity and drag and draw the plot like this. The solid line is the experimental data, and the gray line, the gray band, is the calculations with the experimental parameters. And two things they are saying here is that first, they agree this with this well, and no free parameters. And the second thing is they can use this to estimate Hawking temperatures in the other ways. So they get another Hawking temperature, which is close to the Hawking temperature they estimated from the surface gravity, which is I mentioned earlier, is a gradient of the density, the sound speed, and the speed of the the potentials. And this is simulations. So in this paper, they show the evidence of Hawking's partner correlations and the temperatures. Okay. So any questions so far?
I'm curious, when you measure the Hawking radiation, what do you exactly measure? Because you want to measure phonons, so. Yeah.
So what they exactly measure is this density correlation. It's basically just this is X and S prime just a parameter at a different location in 1D. They have a 1D gas. And
the measure is very similar to what we do. We measure density fluctuations.
Okay, and then do some Fourier transform of that.
Actually,
yes.
they don't do that. Actually, they do 2-point correlation.
Yep.
Okay. Yeah, thank you.
This is 2-point correlation, and G2 here is a fluctuation. This is density fluctuation and at x and at x prime. For G2, they do have an ensemble average of density fluctuation, but this figure is a 2-point correlation.
Okay. Yeah.
And experimental size actually is just one more information to me, or maybe some of you are interested, is that how they handle the data is kind of, again, I'm not very comfortable with that, is that at both figures, they remove a constant background, a DC, a constant, which makes sense for me because we know in some small fluctuation or in some noise, you will contribute in a constant background. But they also remove a background with Gaussian distribution. And I don't know why, but it is in their supplemental, in their method. And this doesn't really make sense to me because what you are seeing here is already remove that Gaussian background. And that Gaussian background, they don't have any explanation why they want to remove that. Okay, this is the first part, and I'm going to the second part. The second paper is, oh, sorry, before I go there, is since they are able to measure the Hawking and the partner inside the event horizon, so intuitively, yes, the next step they are going to do is the archive paper I'm going to talk about is they are able to measure this mode with time evolution. They have time resolution of that. And in simulation or in theory, what people are expecting, there are some modes could be seen in this signal. This is event horizon. This is outside black hole. This is inside black hole. Okay, so we have a D2, which is a co-propagating mode we mentioned. The D1 is a partner mode. So in correlation functions, density correlation functions, what would be seen is the Hawking and its partner, which is UD1, D1, D2. Oh, am I?
Are you writing something? I don't know.
Oh, sorry. This should be wrong. So D2 should be the color code here. I think I messed it up. This is a partner. This is co-moving. So this is Hawking and its partner. This is the real signal. And this is the D1, D2, these two modes, Hawking partners and the co-moving mode. And this is Hawking and its partner mode. And it's positive because it's positive energy and positive energy. So this is positive correlations here. Okay, so this is the Hawking radiation, in my opinion, we are really care about. So this is a simulation, looks like this. Okay, and this is an experiment they have in time evolutions. Very noisy, but we will see the data very soon. Okay, so the next one I'm gonna talk about is this archive paper, which basically follow everything we just mentioned, but with time resolution. And in this paper, they are gonna resolve 3 kinds of modes. And first mode is the Hawking radiation we are talking about all the time, which is the Hawking particle and its partner and generated presumably by the vacuum fluctuation. The second mode is a black hole laser, which is when these the mode travel, the partner mode travel and hit the inner horizon, which is another boundary we will see soon. And this boundary is actually because experimentally, this is a low sound speed, right? And this is back to the high sound speed as this part. So this is kind of has another interface like this part. So when this sound mode or phonon refract by this another inner horizon and bounce back, and it will becomes another collective excitation and go up becomes a lasing mode. And a third mode, which they call monochromatic systematic Hawking radiations. If probably anyone can tell me or not, whether this is a part of Hawking radiation, one kind of Hawking radiation. Basically what they say is that, since this inner horizon is also moving, so there's another mode coming from this horizon. And when they travel to this black hole horizon here, it becomes a Hawking radiation. And why there are another boundary here is we will very soon see is that because the laser tracing, the repulsive laser tracing has a finite spatial width. It's like has only this size. So we know in the co-moving frames, the flow is like flowing like this, and this laser is dragged. This is laser dot. You can take like this. This is a laser dot. So this is a part without laser. So naturally, there's another inner horizon here. Okay.
But sorry, I don't understand if you are inside how you can. You said you cannot move to the left. So what's?
Yes. I'm sorry, I don't know the answer. I have the same questions.
So well, since you say you don't have an answer, so
yeah,
I have the same question to Cheng-Han also. So I'm not sure that mode, that reflecting mode actually can reach the horizon. I don't think it can, but they can measure what's excited inside the horizon because, well,
It could be an exponential maybe, and it decays exponentially, but it still doesn't vanish at the horizon.
Because so supposedly the flow is blowing away from the horizon. So if you have anything reflected from the inner horizon, there's kind of no. Conceptually, I don't think there's a way that mode can propagate towards the left and then reach.
I know, but no, I'm saying something naive, like instead of being a real k, it could be imaginary k, so it could be e to the minus kx. So that will still decay exponentially, but if it's not too wide, it might have some amplitude. I'm not sure I'm making this up. I mean, it depends on how wide is this region.
But well, what they claim to measure is actually some real modes. So,
but on the left or inside? Inside they measure real modes.
Yes.
Okay. K in. Okay, I don't know.
I honestly don't know. In experiment in this busy experiment, I don't think phonon can travel through this. It doesn't make sense to me. But I couldn't. Yeah, I don't know. What I can show you is that.
But do you know how wide that region is?
It's not.
How many wavelengths? I mean, how K? What is K?
We can look at the early paper they have here. So this is a reverse, like a mirror image. Now here is outside black hole. This is inside black hole. Now this is inner hole, and this is event horizon, and flow like this way. And outside the black hole, there's only one mode, positive energy here. And inside there are two modes, positive energy and negative energy here. And this is a co-moving mode, and this is the Hawking radiation mode. But in this paper, they do say if you will travel toward this, which in time-space diagram doesn't make sense in this experiment because we are dragging this boundary actually. And in here, I think what Cheng-An say is right, is they probably because they are able to see modes inside here. I don't see modes travel outside. This is because time evolution. So this is a event horizon, and this is the laser they mentioned. So it's probably just a collective mode inside, still inside here. That's just one explanation. Perhaps someone can tell me whether it's right. Yeah. Sorry, I'm also confused about this part. So let me move on. So back to this. This is all from their archive paper. The quality is quite bad, but we live with that. So this is time evolutions from top to down, and this is the oh, I forgot to label. This is here. This is the potential, and we already in a co-moving frame. So the step moving from here, so the flow from here, from left to right. Okay, so like I mentioned in earlier slides, that there's actually very big global harmonic trap, and the event horizon or the repulsive step potential is actually very tiny compared to the entire thing. So the entire particle is every particle, the atoms are experiencing flowing and free fall, like water flow for all these potentials. And this is a density they convert from the images. And this blue dot is the event, the inner hole they see, because when they compare the velocity, because when the velocity back to when the velocity c faster than the dragon speed, that means it becomes another inner horizon. Then this is a place they see, and this is a velocity they converted from other data, but as you can see, this is so noisy, so they are actually not used. They are not using this for their final calculation. They use oscillating horizon for their dispersion. But I think this is the reason why they need that preliminary test to get the dispersions, because this is kind of not reliable. And this is back to the density correlation function, but here is the oscillating horizon experiment. That means this is when they oscillate the horizon with certain frequency. They see, okay, as time evolve, they see some correlation start to develop, and they map to what they are expecting. That's all I can say. What they oscillate in the horizon with different frequency, different condition, and map to the different regions. So with this, what they did is actually they compare the signal. On the left is the oscillating horizon experiment. On the right is without oscillating. So they compare the signal, left and right signal, and they say, okay, initially there's no Hawking radiations, barely no. So there's actually should be no or very small signal here. And later they start to develop this spontaneous Hawking radiation, which is the Hawking radiation we are talking about. And later, the mode they say, which is much stronger, is Hawking, no, the black hole lasers. And then is the stimulated radiations here. They compare. So this is, to me, this is, they know what they want to look. They do the signal and they find the corresponding place and take it as a signal to analyze. And this is a time evolution. So then they convert the signal to a temperature. And I have to say, I don't fully understand this figure. Maybe someone can comment. So initially they see pretty much not much things. And the green dot is the signal, the signal, kind of signal strengths they convert into phonon mode or phonon population maybe. And so the green dot is the measurement of the strength. I think it's a strength. And the blue dot is the temperature convert from simply the surface gravity. So this is the temperature of the black hole basically. And I don't know about the red part. The red part they say is a width of emitted spectrum. Honestly, I don't know what's this. And so initially in the first 100 milliseconds, they see the developing of the modes and the signal. And then later they see only one they see only one modes, and these modes corresponding the surface, I mean, agree with the surface, the temperature from the surface gravity, which the spontaneous Hawking radiation and its partner. And later you'll see the signal becomes much stronger. It's because they start to develop the black hole laser. And later they have one more terms coming from the stimulated mode from the inner hole. So this is actually the dominant mode here. And the blue is simply from the gradient, the surface gravity. So the slight difference is just because experimentally the gradients of the density and the gradient of the velocity changes a little bit. And so what they see in the final plot is that this is the same figure as we have seen in the previous 2019 papers. They have these modes, and this is simulations, and the F is the artifact from the simulations. And they extract this with time evolution. This is time evolution. So initially they see this is G2 function as we have seen. This is a part similar to the data we see in the previous paper. Actually very tiny negative G2 correlations. And as time evolves, you see this a strong oscillation in G2 and the multimode. Here multimode means multi-frequency. And then evolve becomes just sinusoidal frequency of the G2 here. And this again is a Fourier transform of this green box. And this is in the early stage corresponding to the Hawking and Hawking partner. And this is similarly the line from the oscillating horizon experiment, Hawking and its partner, and Hawking and its co-propagating modes. And what they are saying is that, okay, yeah, the signal, the correlation function in K-space signal is aligned with Hawking and its partner. And later, they also calculate the stimulating mode, and they say, yeah, this is aligned with kind of stimulated emissions. I think this is the data they have shown, the evidence they have shown. Any questions so far?
Cheng-An, I think you need to speed up.
Yeah, I'm done. So the last slide is that so I'm working an experiment, and today I'm talking about is more related to experiment. It's pretty much everything discussed in the paper. They focus very much on the experimental side, and I think this is pretty interesting, because it's kind of combinations of astronomy, quantum mechanics in coherent experiments, and which in a sense that you can use phonon to simulate things happening in photon in a real black hole. And because speed of phonon is something we can manipulate, and it's easier for us, or this is probably the only way we can do for analog or sonic acoustic black hole. But here in Purdue, I think we can do better if we, in this kind of projects, because we are using a platform that first of all, we have a box trap, which the density is homogeneous everywhere. And at this point, I think we are quite confident that we have a decent homogeneous atomic density. And the way we create the horizon, if we want, will be engineer the sound speed directly. because we are using a species of cesium, and we can change the cesium interaction, and the sound speed in this coatom is like this, the density and the interactions. Basically, we change the term of these three. So our goal, or one of the function we are currently working on, is that we will be engineering the spatially controllable interactions. And in this sense, we will be able to engineer spatially change of the sound speed. So basically, we get rid of the trouble of all these density flow and all these basically very noisy part. And I think so what would be interesting will be I think if we can look at the spectrum of the Hawking radiations and try to figure out where does the entanglement goes, because one evidence which I did not emphasize is that they emphasize this temperature or the spectrum is purely thermal. That means a given Hawking temperature determined by the horizon, and you have a temperature, and you basically you can you see a thermal radiation, a black body radiation. And in our system, I hope we will be able to measure the phonon entanglement. Then we should be able to find out if the partner fall into the event horizon inside the black hole, and where is the information, where the information pair does. That's a naive idea, and I'm interested. And any questions? This is my last slide, and maybe people can comment.
Yeah, Cheng-An?
Yeah.
Yes, so in the beginning you said something about there being an information paradox in this case as well. So what is the what is the information paradox for the analog, this analog black hole?
Well, information paradox I mentioned is for a real black hole. That's what I understand. Let me know if I'm wrong, because I know very little about the black hole. So one way we can utilize this analog system is that we can measure the phonon inside the horizon. So that's something in a real black hole. There's no way you can do in a real black hole. So if we can do that, then that potentially I think we'll be able to solve.
Wouldn't you just find that the phonons are entangled? And I think that's what you'll expect as well.
Well,
Yes.
I guess what you're saying is that if you have a phonon outside the black hole that's entangled with another phonon, also outside the black hole, now that phonon travel into the event horizon, will the phonon that's inside the horizon remains entangled?
Entangled, yes.
Down by one, right?
Yep. It will be interesting to see either answers. Like if it's entangled, then why outside the black hole we see thermal spectrum? And if not, where or when does the entanglement disappear?
Okay.
But I guess by construct an analog black hole, we kind of already know the answer, right?
Yeah.
By construction for an analog black hole, we kind of already know the answer. That what I mean is that I think it will remain entangled.
Mm. Yeah. 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 So yeah. So the last piece I just want to say, here in Purdue we have the ability to do these things soon, and by just tracing a laser. This is a laser tracing part, and we can do different things and not limited in just a black hole. I think it could be some related topic we can know, or we can use this to know.
I'm sorry, I actually have to run off to the next meeting. So it's a nice talk. Thank you.
All right.
Yes, so is there any other questions? Yeah. I mean, we have some time, in principle.
Or if anyone has, does anyone have some interesting idea if we have this kind of platform? I believe we will have in the experiment, but like say black hole, analog black hole has been done in these papers from this group, but I think it's probably something we can still use.
So, well, I do have a question. Well, how did they make the event horizon move and oscillate? Say initially, they just have a non-uniform density profile.
Yes.
Then at some point, they will let the non-uniform the non-uniform trapping potential move. Okay, so there is a bump, right? There is a bump in the external potential, and then they are actually just removing the external potential.
Yes.
So okay, then they fix. So did they gradually increase the velocity of the external trap, or is some kind of quench experiment? So they suddenly increase the velocity of the external trap from 0 to a targeted value.
No. So what they did is that let me use this maybe clean. So they address another laser and create this step potential, and they just drag it. And for the initial preliminary experiment, when they drag it, they oscillate like this. When they drag it, they oscillate. And the real experiment, they just drag it with a constant speed. So the real
that constant speed, that constant. My question is that constant speed is turned on instantaneously. So they didn't gradually increase the constant speed from 0 to a final value, but somehow they just turn it on.
Right. More specifically, they drag it from outside the condensate, drag in, but the velocity they use for the V is actually not the speed they drag. The speed that V they use, they need to convert. I did not put that figure. They convert it with the density, with all the dispersions to convert so that they get a real, what the speed the atoms really see. So that's the reason that a lot of work. I think that's the purpose or so part of the purpose they do need this dispersion because they drag it, but that's not, like you said, that the density of the atoms are in the global trap and density are inhomogeneously. That changes a lot of things. So the speed they do in the calculation or in the final plot is already converted.
So we understand this part, they have to convert basically the velocity of the potential to the velocity of phonemes. Okay. But my question is really related to a fundamental issue. Okay, basically here, where they have done some measurements, but whether or not their results depend on how the event horizon was formulated. Well, theoretically, we know that it really depends on the commutation between the sound velocity and the velocity of the fluid itself. Whether or not this difference is established simultaneously, whether or not this difference was established instantaneously or gradually, whether or not these may make any difference in their measurement.
I don't think they change this parameter, but answering if the phenomena happens instantaneously, the answer is no. Initially, they don't see anything. So they claim this is the developing of the black hole, real black hole. So this stage line is they somehow plug their experimental parameter into real black hole equations. So it's like when I don't know, I just very undergrad level knowledge is that when the mass is increasing, and you start to get more and more Hawking radiation, this is the time evolution of that Hawking radiation. And they say, okay, this matches with their experimental data. But the dragging begins, horizon forms at t equals 0. But initially they don't see anything until here they see Hawking radiations. Yeah.
So in this plot, when t is 0, so the velocity of the horizon is already fixed. So it didn't further change it.
Right.
Yeah. Thanks.
Any question, idea, comments?
Okay, so if there are no more questions, we thank Cheng-An, and hopefully you have a good time there, and we'll see you when you come back. Right. And I guess we won't, I'm not sure, maybe we will have some other journal club before the end of the year, or not, we will see. But if not, we restart when the semester starts, which is around January 10, I guess. Okay, maybe I'm gonna. Okay, thank you, and thanks everybody. Bye.
Thank you.
Bye.
Bye.